Now we'll move to our next speaker, who is Dr. Akram Touil from Maryland University from the US, who will be talking about quantum Darwinism and the inevitable classicality of open systems. So you have the mic. Yeah.
Okay, can you see my slide right now?
Yeah, everything is good.
Okay, cool. Thanks. Okay, so first of all, hi everyone, and I would like to begin by thanking the organizers for the invitation and also thanking the organizers for putting together this great event, and I'm really happy to be part of it. And hopefully in the next editions, we'll all see each other in person and discuss some physics. So today my contribution to this event today will be titled Quantum Darwinism and the Inevitable Classicality of Open Systems. So during the talk, I'll give you a general overview of the framework of quantum Darwinism and how it can help us understand the emergence of classicality from quantum principles. And I'll also present a few of our results that we have within this framework. But first, I just want to start by just illustrating the problem. So it is the problem that we're trying to solve, and this can be nicely done in one of Wojciech Zurich's old papers. It's a sketch. And the problem is the connection between the quantum and classical. And this was a problem since the inception of quantum mechanics and still an open problem to this day. And the question here can be basically stated as follows. So how do we understand or how do we reconcile our everyday observations of the classical world around us with the underlying quantumness of nature, with underlying quantum features that are directly at odds with our classical intuition? And those features are comprised of things like quantum superpositions and entanglements and so forth. And the famous or infamous, depends on how you want to look at it, example for that is Schrodinger's thought experiment, where you can have a cat being at two positions or two states at the same time, in this case being both dead and alive at the same time. And to tackle this kind of infamous problem between the boundary between the quantum and classical, one might look at the so-called quantum to classical transition. So that's when a quantum system is inevitably acted upon by its environment, and from this interaction between system and environment is what drives the system from being quantum to classical. And to understand, or basically this emergence of classicality is what's explained directly within the framework of quantum Darwinism. But before I talk about the big picture, I just want to define first a preliminary notion that is really a key part of, or an important piece of the puzzle here, which is quantum discord. So the first part of the talk will be kind of the technical part, where I'll be mentioning or defining what we mean by quantum discord and how this quantity can actually quantify quantum correlations. So basically a way to quantify how quantum are the correlations in a given state. And from this, we'll be looking at the mutual information, how this quantity can account for correlations beyond entanglement, which is important. So once we have this preliminary notion defined, we can now talk about quantum Darwinism, which will be the kind of conceptual part of the talk. So that's the second part. We'll be mentioning pointer states and notions such as objective reality, and also redundancy of information or proliferation of information in the degrees of freedom of the environment. And at the end of the talk, I'll give a take-home message and a couple of open problems that I picked here just to, because they're interesting, or because they are kind of the big open problems that we're thinking about right now. So here, this kind of technical part, I'll try to be careful and define all the terms that we have before we move to the conceptual part of the talk. And the results that I'll be showing today are based on two papers currently in the writing process. So hopefully you'll get to see them soon in the archive. And my collaborators for this project are Benyan from Los Alamos, David Girolami from Polytechnique University of Turin, Sebastian Defner, my PhD advisor from UMBC, and Wojciech Zurich from Los Alamos. And these ideas, so the whole framework of quantum Darwinism really began with the pioneering work done by Wojciech and his collaborators, I think about 20 years now. So for the first part of the talk that I mentioned, which is quantum discord. So I mentioned that we'll be looking at the mutual information. So in this slide, I'll just give you upfront the full definition, or kind of the big picture definition of quantum discord. Basically, by looking at classical information theory, there are two equivalent definitions of mutual information, but their analog definition in quantum information theory are not equal to each other. So the discrepancy between the two quantities is what defines quantum discord. And basically, as the name suggests, it is just the discord between these two quantities. So this is kind of a big overview of how it's defined in a few sentences. But now for a little bit more technical detail. So namely, if we look at classical information theory, and by considering two general random variables, X and Y, we can account for the uncertainty in X through Shannon's information or Shannon's entropy, which has the following form, minus the sum of Px log Px. And one can also define a conditional entropy in this case. So this just accounts for the uncertainty in the variable X, given the knowledge that we have on variable Y. And from these two definitions, so the conditional entropy and the entropy of X, we can get our first definition of the mutual information between the two random variables.
Akram, it seems we lost you.
Some information about your variable Y. So at the beginning of this process, you have some initial uncertainty of the variable X. And at the end of this process, you have this new uncertainty that is conditioned on your knowledge of variable Y. So the difference really between the two in this physical process is the uncertainty lost within the process, which is the information gained. So that's why it quantifies the information that X knows about Y or Y knows about X. So this is a basic definition in classical information theory. So now from basic rule of probability, so basis rule of probability, we can get another equivalent definition. So now we don't have to write things in terms of conditional entropy. We can write everything in terms of Shannon entropy. And here I note this one as I, even though they're both equal to each other, because we'll need to make the distinction once we start talking about quantum systems. So if we shift now gears to quantum information theory, and the whole idea is that instead of considering random variables, we'll be considering the states of two quantum systems. So here I'm just considering generally two quantum systems, S and E. Afterwards in the talk, I'll mention specifically the physical meaning, or kind of the physical distinction where one is the system and one is the environment. But for now, or at this part of the talk, this is just two general quantum systems. And the whole idea in quantum information theory is that the analog definitions of the quantities that I mentioned, J and I, are not equal to each other, generally speaking. And this is due to the fact that once you start talking about conditional probabilities or conditional entropies for quantum systems, you also need to specify the measurements that you're applying on your quantum systems. And measurements do generally disturb the states of quantum systems that we probe, and that's why we do not have this equality anymore. And the easiest quantity kind of to extrapolate to quantum information theory is the I that I defined earlier, where now it accounts, or it's referred to as quantum mutual information, where now instead of accounting for the uncertainty in the state of a random variable through Shannon's entropy, we account for the uncertainty in the quantum state through what's called the von Neumann entropy, which is a generalization of basically from a big picture perspective, it's a generalization of this notion of Shannon entropy to quantum information theory. And this is just a general form of it. And the other quantity J now also depends. So the quantity that was written in terms of conditional entropy is now dependent on the family of measurements that we apply on E to learn about S. So in this scenario, it's the same physical interpretation that we had before. And in this scenario, we have a bipartite quantum system, and we apply this local measurement on E to learn about S. So we're actually getting the classical correlations of the classical information from this quantity. And now for the definition of this code is simply defined as the difference between the two quantities. So just the difference between the quantum mutual information and this quantity for the family of measurements. And for as a technicality, we here need to optimize over the set of measurements. And what I mean by optimizing in this case is just you pick the set of measurements that maximizes this quantity J. And I'll refer to it during the talk as the Holivo bound or the Holivo information as referred to in the literature. So, and also just a small piece of notation here that I'll adapt throughout the talk. I'll keep this kind of a check mark over the quantum system that I'm measuring, I'm optimizing my measurements over. And from the definition, basic definition of discord, quantum mutual information accounts for both quantum and classical correlations, and the Holivo bound or the Holivo information accounts only for the classical part of those correlations. So basically a simple definition is the difference between the two quantifies the quantum or purely the quantum correlations in the system. So that's kind of a mathematical quantity that quantifies how quantum the state is, if you want to look at it that way. And before I move to quantum Darwinism, I just want to mention three general properties once we start talking about this quantity. So the first property is really by construction, discord is always positive. So basically it quantifies quantum correlation. So it's either zero or it's either strictly bigger than zero. And the second property is that discord is zero if and only if the pre-measurement state is equal to the post-measurement state. So this is the state, the quantum state, or the composite quantum state before we make any measurement. And this is the composite quantum state after we apply our measurements. So this is just physically meaning that discord is equal to 0 for measurements that do not disturb the composite quantum state. And the third, which is more of a comment really than a property, where for separable state, so for state where you don't have any entanglement, you can still have discord different than 0, which was really the core idea of why discord was defined, because here it shows us that discord can quantify correlations beyond the entanglement. And for the experts in the audience, you can look up the original paper by Olivier and Zurich for kind of the derivation of all these properties, and also the specific example picked for the separable state that still have discord in them. So that was it for the kind of technical part of the talk. And just for a quick recap of what I mentioned, what I've given you so far is just a mathematical definition of quantum discord and how this quantity can be defined just basically from contrasting the definition of the mutual information in both classical and quantum information theory, and how this quantity can account for correlations beyond entanglement, which is really important. And what we aim to achieve now is basically framing this quantity in a nice physical context, and that is for the emergence of classicality. So how can we understand these quantum to classical transitions, and what can it tells us about the connection between the quantum and classical? And all of this is done within the framework of quantum Darwinism. And the first step for this framework is decoherence theory. So the first step that we need to talk about, which is a necessary but not sufficient step to describe the emergence of classicality. And to also, for completeness, to define my terms. So decoherence is the basis-dependent process of loss of quantum coherences. And that's the process by which you get the destruction of the off-diagonal terms of your density matrix. And generally, you get this from an open quantum system that is inevitably acted upon by its environment. So the kind of setup I'll consider for the remainder of the talk is interacting with its environment such that the state or the composite state is pure here. So this condition can be relaxed, but I'll stick to this condition for the talk. But what I want to get across is that this is not really a constraining condition, in the sense that what I really mean by the system plus the whole environment is that it composes the quantum universe, and we only have access to the system plus some small fragments of the environment. And this will be a little bit more clear in the following slides. But the whole idea is this quantum universe can be described by a given wave function, so that the whole state is pure. So it's kind of justifiable to make this assumption. And back to decoherence theory. So the whole idea from decoherence theory, from a general viewpoint, is we trace out the degrees of freedom in the environment, and we only focus on the reduced dynamics of the system of interest through your master equation of choice. So it depends on how you model the system environment interactions or how you model the environment itself. But the conceptual picture to keep in mind here is that the environment in decoherence theory has this passive role of being a sink for information, in the sense that we're tracing out the degrees of freedom in the environment, and we don't have access to the information that the environment contains about the system from their interaction. And this is not what happens in real life, and this is not how we carry out our everyday observations. And basically, this is where quantum Darwinism comes in. So quantum Darwinism recognizes that we need to incorporate the environment's degrees of freedom into our theory. And now the environment is promoted from being the sink for information to being an actual witness to the information contained in the system of interest. And the perfect example for that, I would say, is the photon environment. So right now you're able to see my slide, not by some sort of direct interaction with your monitors, but you're actually capturing the photons emitted from your screen. So that's how you're able to infer the information that I'm presenting in the slides. And the core idea of quantum Darwinism is that this sense of emergence of classicality is really a byproduct of us observers eavesdropping on fragments of the environment. And also I'll explain this in the next slides, but just to put in exact words, the objective that we have within, or the objective of the results that I'll be presenting today, is to quantify exactly the information that can be obtained from fragments of the environment. So the three main quantities to look into, the mathematical quantities to look into in this case, are the quantum mutual information, so the quantities that I talked about kind of briefly at the beginning of the talk, the quantum mutual information between the system of interest and fragments of the environment with m degrees of freedom, and also discord when you make measurements on these fragments of the environment, and also the whole level bound. So this quantity, just as a reminder, so this quantity quantifies purely the quantum correlations, this quantity quantifies purely the classical correlations, and the quantum mutual information is the sum of both, which quantifies the total amount of correlations in your bipartite state. And this is in direct contrast with the other quantities that were already discussed in the literature, where you make direct measurements on the system of interest instead. So we're looking at these quantities as our main quantifiers. But just to go back to the big physical picture of quantum Darwinism and to drive home this physical idea, one can look at these quantum to classical transitions as follows. So you start with fragile quantum states. So you have a quantum system that is inevitably acted upon by its environment. So you can think of this as your quantum computer that is always prone to outside noise from the environment. And from this interaction, you get some pointer states, or some few selected states are able to survive the process. And pointer states are generally defined as states robust to decoherence. And the whole idea is, this process was coined ion selection, which is short for environment-induced superselection. And these pointer states are entirely determined by how the system is interacting with the environment, without going into the mathematical details. But the core idea to emphasize is how to move from this notion of pointer states to a notion of objective classical robust states, or what I'll be referring to during the talk as notion of objective reality. So objective reality, or to define it exactly, is when independent observers, so as us, as classical observers, can simultaneously access information about the system of interest, and they come to, or they reach consensus, and that's the big idea. So when so you have these independent observers measuring different parts of the environment, and they come together and they reach consensus or their measurements, or they agree on their measurements, and that's when we can say we have reached this notion of objective reality, or basically reached classicality. And so now that I'm throwing all these conceptual ideas, it would be interesting, or be more digestible, to actually present this in a nice physical setup. And that's just a simple setup that we picked for our paper. So the setup is just a single qubit interacting with a many qubit environment. And for simplicity, the many qubit environment begins in a pure state. So here, for technical details, all the 0 states, so it's all up state for the environment. And the central qubit begins in a superposition of 0 and 1 that we can easily parameterize here. And as a direct analogy to our photon environment, where we get most of our everyday information, where actually to the energy scales that we are interested in, photons do not interact with each other. So our qubits here do not interact with each other. And the only interaction we have is between each qubit of the environment and our central qubit. And we model this interaction with what we call an imperfect CNOT operation. And just to explain it, we can focus on a single qubit from the environment and our central spin. So if the central spin begins in the 0 state, so we're not affecting the state of the environment, similar to the CNOT operation. So the state of the environment stays 0. And if the central spin begins in the 1 state, then we rotate the state of the environment into a superposition of 0 and 1 that we can also here parameterize. And the trivial case of S equal to 0, so that's when the first term just cancels, and we get the CNOT operation that we are all used to. And here we are kind of parameterizing this, or modeling this imperfect CNOT, because through this modeling, we will have the ability to tune and actually change the degree with which the environment qubits are monitoring the central qubit. So how much information they're getting out of their interaction with the central qubit, which is important. And now to go back to kind of the big ideas of quantum Darwinism and explain them within this framework. So the first one that I mentioned is ion selection. So what happens from ion selection is you get a system interacting with a general quantum system interacting with its environment, and the end state would be this branching wave function that has specifically 2 branches, and these branches are determined by the imperfect CNOT that I mentioned earlier. And I'll be talking about the example of p equals to 1/2. So just as an illustration, at the very end of the talk, I'll mention briefly some kind of surprising results once you actually start changing the initial superposition of your qubit. But the main idea, really the star of the show here that we need to discuss, is this notion of emergence of objective reality in this many qubit environment. And the whole idea is, if we actually look or measure a certain number of qubits in your environment, and you measure different fragments, or you capture different fragments, they all reflect the same amount of information, and they actually reflect all the information there is to learn about the system of interest. And this is due to the fact that from the interaction between the central qubit and the many qubits of the environment, there are many copies of the classical information about the central qubit that is proliferated in different parts of the environment. That's how we reach consensus as observers when we measure the environment. And this is actually where the name, or where Darwinism comes from in quantum Darwinism, where these pointer states, so the 0 and 1 in this case, so the pointer states of the dynamics, so those are states able or fit to survive their environment, and these fit states produce information theoretic offspring that are in different fragments of the environments. And we get this sense of emergence of classicality by eavesdropping on these fragments of the environment. So, and the nice thing, we can actually quantify this mathematically through the quantities that I mentioned. So the mutual information, the level bound, and also quantum discord. And just to give you a kind of a big picture how you would expect the mutual information to behave in such a scenario. So in this case, it would be the mutual information between the central qubit and the fragment of the environment with the m qubits. And if we plot this with respect to the fractions of the environment, this is the typical plot that you would get after decoherence had happened. And the interesting thing about the plot is that already for small fractions of the environment, so if you only capture, if you only look at small fractions of the environment, you are capturing almost all the information there is to learn about the system of interest, and changing the number of degrees of freedom the environment you have access to doesn't change much the value of the information that you are getting. And that's why this was dubbed the classical plateau, because this is where you can say that we have reached this objective reality and observers are indeed agreeing on their measurements, on their independent measurements. And just as a technical detail, so this rise of the mutual information, or the eventual rise that we see once we start capturing all the fractions of the environment, is due to the fact that the state of the system plus the whole environment is in a pure state. So due to the symmetry of the von Neumann entropy, the mutual information just jumps to a value of 2hs. So the other interesting thing for this model is that we can actually derive analytic expressions of the mutual information and the Holivo bound and discord when we make measurements on fragments of the environment. And just to give you a brief illustration of our results, so I picked here the case of n equal to 100 spins. So you have a total of 100 spins in your environment, and the plateau, the value of the von Neumann entropy of the central qubit is just equal to 1. So I'm plotting everything in the log2 basis, and I'm plotting for different values of c. So this parameter c or s, they quantify the degree with which the environment qubits are actually monitoring the central qubit. And as expected, once we start increasing the value of c, we start seeing more and more pronounced plateau, in the sense that for, let's say, for this green plot here, you only need a smaller and smaller fraction to actually access all the information in the central spin. And this is due to the fact that the closer c is to 1, the closer we are to a perfect C-naught operation. So in the C-naught operation, we get a GHZ state, again, for the experts, without going into the mathematical detail. From these GHZ states, basically any spin that you pick in the environment can give you the full information about the central qubit. And now for the interesting quantities, that is a discord and the Holivo bound in this case. So when you make actual measurements on fragments of the environment, and I want to explain this behavior by contrasting it to the other quantities that were discussed in the literature, namely when you make measurements on the qubit or the central qubit instead of the qubits of the environment. And first, the first thing that I want to notice here, or kind of point to, is the similarities between the plots. At some point in both plots, so once we start capturing enough fractions of the environment, both Holivo bounds, whether you're measuring fragments of the environment or whether you're measuring the system, they both reach a plateau. So you both reach a plateau that is equal to 1 in this case. And for this scenario, discord on both sides is just equal to the mutual information minus the value of this plateau, which is -1 in this case. So both plots eventually overlap with each other for large fractions of the environment. And this increase that we see is directly due to the increase that I just mentioned of the mutual information for large fractions. But the very interesting behavior that wasn't seen before in literature is when you measure small fractions or very small fractions of the environment, you still have discord that is different than 0. And we can actually prove beyond the imperfect C-naught model that I described that the discord being different than 0 for large fractions is basically equivalent to having discord different than 0 for small fractions when you measure these small fractions directly. And this can be directly understood in terms of monogamy relations and trade-off relations that I will not go into the technical details. And for the experts in the audience, this is kind of similar or kind of reminiscent of the Kawashii-Winter relation in the quantum information theory, but here we're proposing a trade-off relation between quantum discord and the Holivo bound. So purely quantum correlations that can go beyond entanglements, and not unlike the Kawashii-Winter relation, which only focuses on the trade-off between the entanglement and the classical correlations. So now the very last thing that I want to mention for the talk is what would happen to all these quantities if we change the initial superposition that we have. So if we change how we prepare our state initially. And what we found is that, generally speaking, if you change the value of P here. So that's the parameter that quantifies actually the initial superposition. That changes the value of the classical plateau. So basically by a simple rescaling of the plot, so if you rescale the y-axis by dividing by this value of the plateau, you can quantify the kind of the overlap between the two plots by simply the difference between the two quantities. And we can do the same thing. So here I'm presenting for the mutual information, but one can do the same thing for the whole bound as well. And what we found is that we have a universal behavior that is quite insensitive to changes in values of P. And we only see some limitations or breaking of this universality for small values of P. And I can illustrate this in a brief kind of plot here. If we plot different values of P here, we only see differences or kind of breaking of this universality once you get P closer to 0 or P closer to 1. And those are really not interesting in our case because you're just starting with a pointer states of the dynamics. So it's not affected even by the interaction with the environment. And also, if we only focus now on the initial rise of these quantities, so now either the mutual information or the believable bound, we found, which is a much surprising effect, is that it becomes actually insensitive to changes in the total number of degrees of freedom in the environment. So this all goes to show this universality of this behavior that I'm describing in quantum Darwinism that can be extended to other models actually. So now for kind of a take-home message or summary for the talk, you can forget all the technical details that I mentioned and remember these three main points of the talk. So the first one is these quantifiers from quantum information theory, such as quantum mutual information and quantum discord, are really useful in understanding these kind of foundational problems that are basically connecting the quantum and classical. And the second point that I want to mention, which is really the core idea of quantum Darwinism, is that the environment now is no longer a sink for information as it was described in decoherence theory, but really it is an actual witness to the information contained in the system. And this, as I mentioned, is something we are familiar with on a daily basis because most of the information we get about the world around us is from the photon environment. So essentially the environment now is a communication channel for the information about the world. And the quantities of interest that need to be probed in other models are quantum discord, when you make measurements on these fragments of the environment, and also the Holivo bound, when you make measurements on fragments of the environment. And just as a technical detail, so in our work, I mentioned here optimal measurements, but one can also pick cases like random local measurements or really inefficient measurements, and you can still reach this plateau in the Holivo bound, and you can still reach zero discord, showing this emergence of classicality. And the third take-home message, which was actually the very last thing that I spoke about, is that these quantities, these mathematical functions, have this universal behavior that can extend even beyond our model. And actually, for the photon environment, which is the more realistic scenario, our analytic expression of the mutual information is directly is the same one for the photon environment. It's the same as the one you would get if you have a photon environment and you actually derive it through scattering in your photon from superposition of quantum states. And the two main open problems now that I want to mention, which are actually the problems that we're currently thinking about. So the first one is we were really able to quantify analytically and also numerically quantum discord in our case because of the structure of the branching state, the structure that we get from the interaction between system and environment. But if you increase the dimensionality of Hilbert space, and if you have a much more complicated scenario, it would be really intractable, even impossible optimization problem to figure out what is the optimal measurement that would quantify discord or the Holivo bound even. So it would be interesting to get a measurement independent quantity that would give us similar physical picture as discord, but not as complicated numerically or even analytically as discord. And the other problem is really what I've shown you so far is everything after decoherence had happened. So it would be interesting to include some dynamics into this idea, or this idea of emergence of classicality, and basically studying quantum Darwinism from a dynamical perspective. And this can be done through kind of an information dynamics perspective. When you look at the problem, the moment the quantum system is entangled to its environment, so that's basically the spread of quantum information between system and environment, and the eventual copying of classical information that you get at the end, which is responsible basically for the emergence of classicality. And with that, I would like to leave you with this kind of general scheme, how to picture these quantum to classical transitions. And the whole idea is that we start with some fragile quantum states. And from these fragile quantum states, we end up with objective classical robust states. And as we already saw in the nice talks that we had today, so quantum features such as superposition and entanglement are really useful in quantum technology, such as quantum computers, so they can be used directly as a computational resource. But the message that I want to get across here is that they're not only a computational resource, but they're actually responsible for the emergence of classicality as we know it. So the emergence of objective reality that we observe on a daily basis is due to these weird counterintuitive features of quantum mechanics. And with that, thank you for your attention.
Thank you so much, Dr. Akram Touil, for this amazing presentation and amazing results. The talk was about the quantum Darwinism and the inevitable classicality of open systems. I think we have a lot of nice questions here in the chat. The first question is from Osama Hurhu. Do you results? Okay, I have a question regarding your setup of the environment of qubits. Do your results change when the initial state of the environment is unknown?
I should have actually put the top. Yeah, that's actually a great question. So let me see directly where. Can you see my slide right now? So you can see
yeah.
it, right? Okay, cool. So yeah, so here I didn't mention it due to time constraints, but here for simplicity, since where we're going after quantifying information theory quantities where you make measurements on the environment, but in these two nice papers by Zvolak, Kwan, and Wojciech, they actually studied this generalization, but they were looking at quantities when you measure the system of interest. So here we're kind of taking a different picture where you actually, which is the more direct kind of conceptual picture of quantum Darwinism, that you get the information by measuring fragments of the environment. But to answer directly your question, we can directly generalize it to hazy environments or mixed environments, so not necessarily for pure environments.
Okay, thank you. The next question from Khadija El Annous. My question is about the type of measurement that you have used to define your environment. Thank you.
Yeah, so here in this case, or what I presented today is for optimal measurement. So it's basically an optimization problem where if you want to actually just do a brute force optimization, it can become really intractable. But the idea is you pick the measurements that gives you the maximum believable bound, which means just you pick the measurements that gives you the maximum classical information about the system of interest, which consequently gives you the minimum discord. But to kind of avoid doing the brute force optimization, one can use the Kawashii-Winter relation to actually compute analytically, in this case, the Holivo bound. So for your question, these are optimal measurements. But as I mentioned at the end of the talk, we can generalize this to random local measurements, which can go up to 25 spins numerically. So you can do that numerically for random local measurements. But for the analytic expressions, which are valid for any number of spins, you can get it from the Kawashii-Winter relation.
Okay, thank you. Someone is asking, can you please tell us your journey to quantum research?
Sorry, can you repeat that?
Can you please tell us your journey to quantum research?
Oh, okay. So yeah, it's kind of a different question then. So I would say, so my journey, kind of an unconventional one. So I did most of my studies in Rabat, which was in classe préparatoire, lycée Moulay Youssef. After that, I did l'école Mohammediya d'ingénieur. And after doing some engineering, so basically in those years doing internships and stuff like that, I decided to switch to physics because I really like doing physics and math in les classes préparatoires, and that's how I actually made the transition. And yeah, so that's kind of the big picture from engineering to physics without going into the gory details.
Okay, thank you, Dr. Osama, for the brilliant presentation. And hope we'll have you in another event in the future. Thank you so much.
You.
Thank you.